All right, welcome. We are about to begin our lecture on Chapter 8, Lecture number 2. This is a discussion of covalent bonding. Much of this start of the lecture will be stuff you're familiar with from last year's course, in which we investigated Lewis dot structures. We're going to get a little bit more in depth about our understanding of Lewis dot structures and introduce a couple of brand new concepts to you this year. So without any further ado, let's get started. So to begin here today, let's have a quick look at a review for some rules for writing a Lewis dot structure. Recall from last year that a Lewis dot structure is a means for us to model the bonding and distribution of electrons present in a molecule. And you might recall seeing these lots and lots of times last year. In particular, here's a couple we'll draw real quick. This is a Lewis dot structure for a methane molecule, and another one familiar here. This is a chloromethane molecule we'll draw next. And keep in mind that a Lewis dot structure is just a model, and as all models have, there are limitations to what a Lewis dot structure can show. In particular, Lewis dot structures show us a lot of information about where bonds are between which different atoms, and they show us about the distribution of the valence electrons on these different species. But again, there are limitations to what you can show with a Lewis dot structure. So let's have a look here at our outline for the steps for producing a Lewis dot structure. Please be very, very careful in drawing your Lewis dot structures for the AP test. It can be very tempting to save yourself some time and just quickly sketch a Lewis dot structure that looks reasonable. But if you take the time to draw them out and consider each of these steps along the way, that will help you to avoid a bunch of common errors that will end up losing you points on the AP test. So to begin with, for drawing any Lewis dot structure, the very first thing you need to do is to determine the total number of valence electrons available in the molecule. You're going to count up those valence electrons by using your periodic table, and you don't need to go through and do the electron configuration for each of the different atoms present here. I would just save time in your shortcut and recognize that everything in group 1 on the periodic table will have 1 valence electron. Group 2 elements, those alkaline earth metals, will have 2, and then skip over those transition metals because we're not really going to be too interested in those transition metals for most of our covalently bonded compounds we'll be representing here. Then we've got 3 valence electrons present in our boron group, and then 4, 5, 6, 7, and 8 going through the rest of the representative elements there when we end up on the right-hand side of the periodic table of the noble gases. So again, count up the total number of valence electrons available, and if necessary, you may need to adjust the total number of electrons present in the system to form bonds, depending upon whether or not there is a charge on the species. That is, a positively charged cation will have fewer electrons than a neutral molecule would have, and a negatively charged anion will have more electrons than a neutral molecule would have. So again, adjust those electrons as necessary if you're dealing with an ion rather than a molecular species. Step number 2, we're going to go ahead and draw a skeletal structure. When we get to chapter 22 for drawing organic molecules, you'll have a little bit more information about these skeletal structures. But in general, when drawing your Lewis dot structures, a good rule of thumb to work with is to start with the least electronegative element and place that at the center of your structure, and draw the more electronegative elements all around the periphery, around the outside. So we'll draw your skeletal structure, and then let's place a single bond between each of the atoms attaching to the central atom in the skeletal structure. And while we draw these bonds, recognize that each bond represents a shared pair of electrons. So we'll be deducting 2 electrons for each bond that we put into our structure. Once we have drawn the skeletal structure and made our bonds between those atoms, we're next going to attempt to fulfill the octet rule for all atoms. Recall the octet rule tells us that atoms tend to take on an electron configuration that gives them a full set of 8 electrons, that is a full octet, in their valence shells. There again is nothing magical about that number 8 for atoms. They don't love the number 8 for some reason. They don't have hopes and dreams and feelings. Again, recognize that that is a full, complete valence shell for most atoms, and as such, that puts those electrons at the lowest possible potential energy level. There are some exceptions to our octet rule we need to watch out for. Number one, first and foremost, make sure hydrogen will only ever have one bond in any of the molecules we are making for a total of 2 electrons, because recall hydrogen as a period 1 element will have a complete outer valence shell when only that 1s orbital is filled, because there is no 1p orbital present. So hydrogen will only get one bond for a total of 2 electrons. Likewise, beryllium and boron will oftentimes tend to form structures where we see 2 bonds present for beryllium for a total of 4 electrons in the valence shell, or 3 bonds for boron for a total of 6 electrons in the valence shell. For a quick example of a molecule that this will apply to, we might look at something like boron trifluoride. For making a Lewis dot structure for boron trifluoride, we put our low electronegativity boron atom at the center and the 3 fluorines around the outside. We can count up our valence electrons, 7 for each of those fluorines, again halogens, and 3 for our boron, which gives us a total of 24 electrons to distribute to make this molecule. And making our skeletal structure, we'll add single bonds between the boron and each of the 3 fluorines around the outside. That will give us a total of 6 electrons used up to make those 3 bonds, bringing us down to 18 total. And we can now count up the number of electrons we need to complete our octets. Each of the fluorines, again, will still need 6 for a total of 18, and the boron needs 2, which would bring us up to 20. And rather than forming a double bond here, which would be our normal solution to this situation where we don't have enough electrons to go around, instead what we're going to do is go ahead and give the fluorines all of those lone pairs to fulfill their octet rule and leave the boron as an electron deficient element in the center right there. And this seems like it violates our rules, but it does make sense from an energy perspective, because recall when bonding between these 2 species, boron and fluorine, boron is much lower in electronegativity than fluorine, and as such does not have a strong ability to pull those electrons towards itself. So it would seem that the molecule would be more stable at lower potential energy if we were to give all of those electrons to the fluorines for those lone pairs, leaving boron electron deficient, since it really doesn't have a strong ability to pull more electrons towards itself. So again, watch out for beryllium and boron, who tend to form incomplete octets. A couple of other ones to watch out for here are nitrogen and phosphorus. In particular, when a molecule has only one nitrogen or one phosphorus atom present in it, you'll often end up in a situation where it's impossible to make complete octets for all atoms because you have an odd numbers of electrons present. And if there are an odd number of electrons present, in that instance, we're going to have to give something not a complete octet because it's fundamentally impossible. Oftentimes it will be nitrogen or phosphorus that ends up taking on that odd electron. So we got octet rule to be filled. We'll do the best we can to fulfill it. And then we've got a couple of instances if we can't. If you go through and try to fulfill the octet rule by giving all those lone pairs of electrons away, and you find that there are not enough electrons available, at that point you'll have to do what you learned how to do in kindergarten. If there's not enough to go around, you'll have to learn to share, which means forming more bonds shared between different atoms. So at this point, you can add double or triple bonds to help your situation and come up with enough electrons to complete your octet rules. Please remember never to make a double or triple bond to hydrogen, as it only can take 1 bond total, or in particular to fluorine, because fluorine is so electronegative, it does not do a good job sharing extra electrons with other atoms. It more takes them to itself. So hydrogen and fluorine, never expect to see those with a double bond. If the opposite is true and you have too many electrons floating around, in that instance, now you kind of have a problem where you have to find a place to put those extra electrons. In general, we put the extra electron pairs on the central atom to form what's called an expanded octet. And for a justification as to why we might put the extra electrons on the central atom, recall that in making our skeletal structure, usually the least electronegative element goes at the center, which oftentimes is the largest of the atoms in the molecule. And because we're going to be packing extra electrons around that central atom, if we put a small atom at the center and then try and pack a whole bunch of electron density around it by adding more electron pairs, that's going to increase the repulsion between those electrons and therefore also increase the potential energy of our molecule. Recall that molecules tend to form in ways that minimize potential energies of their system, so it would seem more logical to put the extra electrons on the largest atom to minimize those repulsive forces between the electrons and keep them at a lower potential energy level. When we are going to be going through and making these expanded octets, recall that we can only form expanded octets with elements in period 3 or below on the periodic table due to the availability of those d orbitals that show up for the first time in the third energy level, which are orbitals that are available at more or less a similar energy to the valence shell electrons already present and are able to participate in bonding without increasing the potential energy of those electrons to too high of a degree. So yeah, those are our Lewis dot structure rules in general. And please, again, as I mentioned before, make sure that you follow these rules each time you make a Lewis dot structure, rather than skipping steps to a shortcut here to save time, because this is a place where really taking the time to check yourself will help to earn more points on your AP exam. So now that we've had some time to go over the Lewis dot structure rules, which we introduced to you last year in our first chemistry class, let's go ahead and get some nuance to this idea. In particular, I'd like to start by looking at an example here of a Lewis dot structure for an organic molecule that goes by the name of benzene. Benzene's chemical formula is C6H6. And it's kind of an interesting structure in that it is a ring structure molecule. If you remember to last year, it's actually one of the ones you built when we built the ball and stick models of the different compounds in our little in-class activity. So let's go ahead and start by drawing a Lewis dot structure for benzene. We can count up the number of valence electrons present. We've got 6 carbon atoms, each of which have 4 valence electrons. That's 6 times 4 for a total of 24 electrons. And we've got 6 hydrogen atoms, each of which has 1 valence electron for a total of 6. So our 24 plus our 6 gives us 30 electrons to distribute. We'll now go ahead and draw a skeletal structure for benzene. Again, remember this is a cyclic or a ring compound, so we're going to put our ring of 6 carbons here with a hydrogen around the outside of each of those carbons. And we can go ahead and add a single bond between each of the 6 carbon atoms and from each of those carbons to the hydrogen around the outside. And in doing so, we use up a total of, it looks like to me, 24 of those electrons. So starting off with a 30, used up 24, we are down to 6 more electrons we have to fulfill our octet rule and make a valid structure. Now, as we have a look around here and count up the number of electrons we still need to complete our octets, we note that each of those 6 carbons still requires a total of 2 electrons each to fulfill the octet rule. All the hydrogens are taken care of, again, because we only need a duet of 2 electrons per hydrogen. So we've got a total of 12 electrons that still are needed in order to fulfill the octet rule, but we only have 6 available. And in this situation, again, there's not enough to go around, so that tells us that we need to form some more bonds. Something you might have noticed from last year is that each time we make a double bond, it brings the difference between the number of electrons we need versus the number we have 2 closer together. So we need 12, we have 6, which means we need a total of 3 more double bonds between those carbon atoms. And you'll notice here that as soon as I place one double bond, it forces the positions where I place the others. So I end up with this structure of alternating single and double bonds. So now we've drawn a valid Lewis dot structure. But here's something that's kind of tricky about this situation. It's possible, using some more advanced techniques than we use in our general chemistry class, to measure the length between nuclei of carbon atoms, which we refer to as the bond length in this molecule. And as it turns out, when we look at the bond length measured between carbon atoms in a benzene molecule is 140 picometers. Pico is a prefix which represents 10 to the negative 12th. And interestingly, all of the bond lengths are the same within the benzene molecule. But in the structure I just drew, I had alternating single and double bonds. And in other molecules where we see carbon-carbon single bonds, those bonds are usually about 154 picometers in length. And a carbon-carbon double bond is only about 133 picometers in length, which implies, therefore, in benzene, the actual bond length between each of the carbons is somewhere between that of a single and a double bond, and more so, all of the bonds appear to be identical to one another, neither a single bond nor a double bond. And what we've come up against here is an example of a problem with the Lewis dot structure model. Remember, the Lewis dot structure model is in itself just a model. It describes nature, but it is not itself nature. And we've come up against something here that's showing us that our model is not entirely correct. So to help us deal with this situation, we're going to draw what we refer to as a resonance structure. A resonance structure is essentially the use of an average of two or more equally valid Lewis dot structures to more accurately represent a molecule that is not fully described by one of the Lewis dot structures we have drawn. And what I mean by that is if we have a look at our benzene ring here we just drew, notice that I put the first double bond in and that told me where the positions of the other double bonds in the molecule had to be. But if instead I had placed the double bond between these two carbons, I would have ended up with a Lewis dot structure that had the double bonds in totally different positions around that carbon ring. And the real question you really come up with then is, well, which of these drawings we've made here really truly represents the actual structure of benzene? And as it turns out, the answer is really neither of them entirely represents what we observe from those measured bond lengths. Really, the best situation here would be if we could kind of imagine superimposing those two models on top of one another, where we don't really have single bond, double bond, single bond, double bond, single bond, double bond going around the ring of that molecule, but instead we have about 1.5 bonds worth of electron density between each of those carbon atoms. That is to say, an average of the two structures. And remember again, these electrons are not particles confined to one position in space. They are described by a wave function, which is a probability function, which really means those electrons are less localized than our Lewis dot structure model really suggests. And so it should come as no surprise then that the Lewis dot structure model does not entirely describe the nature of the molecule that we're observing here for our benzene ring. So again, if there's two equally valid Lewis dot structures that can be drawn, we're going to represent those as resonance structures, and generally we show the resonance as a set of double-headed arrows between the equally valid Lewis dot structures. Now, if one of the dot structures is better than the other in terms of how it was drawn, in that case, resonance would not exist. It's only when there's no energetic difference in terms of the structures which we have drawn that we'd expect to see resonance structures more accurately capturing the nature of our molecules. So let's take a moment now to work another quick example problem with a resonance structure. In this case, we'll go ahead and have a go at the carbonate ion, that is the species CO3 with a -2 charge. So following along our Lewis dot structure rules, the very first thing we're going to do is count up the number of valence electrons which are available to form bonds. We've got one carbon atom with 4 valence electrons and 3 oxygen atoms, each of which have 6 valence electrons, so 3 times 6 gets us up to 18 for oxygen. And be very, very careful to note here that, again, this is a negatively charged anion with a -2 charge, so we need to add 2 more negatively charged electrons available in the system to reflect the charge on this ion. So 4 plus 18 is 22, plus the 2 more gives us a total of 24 electrons available to form bonds within this species. We'll now go ahead and draw a skeletal structure. Between carbon and oxygen, carbon is less electronegative, so we're going to go ahead and put that one at the center of our species. Again, it kind of makes sense to put the less electronegative thing in the center because that one's going to be forming a lot of bonds, and electronegative atoms don't really share electrons well, they take electrons. So you wouldn't put the kindergartner who's bad at sharing at the center of the circle and make them share with all the people around the outside. And we'll go ahead and put that central carbon atom on there and 3 oxygens around the outside. And we can make single bonds between the carbon and each of those 3 oxygens, which uses up a total of 6 of our electrons we had available, bringing us down now to 18 total. And we'll now go ahead and get a quick inventory of the number of electrons we need to fulfill our octet rule. Each of the oxygens around the outside need a total of 6 for 6, 12, 18 total. And the carbon needs 2, which means we would need 20 total to fulfill our octet rule. We have 18 available, but there are 20 that we need, which means there's not enough electrons to go around. And so just as before, we're going to go ahead and form a double bond in order to get a little bit more electrons available for fulfilling our octet rule. So I'm going to go ahead and choose arbitrarily here this oxygen to form a double bond between the carbon and the oxygen. And when I do that, recognize that there really is no thermodynamic reason that I should choose one of the oxygens over the other to give the double bond to. That is, each of those oxygens is equally electronegative than the others. So really, there's no reason from an energy perspective that one should get more electrons than the other should in this ion. So we recognize that if I choose to put the double bond right there, I can now go ahead and fulfill the octet rule for the rest of the atoms. Go ahead and give out some lone pairs of electrons to the oxygens there. And I've made a valid Lewis dot structure. But I recognize that I chose arbitrarily one of those 3 oxygens to get the double bond, which means I could equally well have put the double bond between the carbon and this oxygen instead, or just as valid, I could have put it between the carbon and the last oxygen as well. There's really no reason to prefer one over the other, which means we're in a situation yet again where we have formed a resonance structure here. So really, there's not a single bond between 2 of the oxygens and a double bond between one of the others in the carbon. Really, what we see here is a situation in which there's about 1 1/3 of a bond between each of those oxygens, or at least 1 1/3 of a bond's worth of electron density would be a better way to put that, between the carbon and each of the oxygens. And no one of these Lewis dot structures completely can describe the actual structure and nature we would observe. Again, because each of those carbon-oxygen bonds should have the same bond length and the same electron density. So really, we're in a situation where resonance is our best attempt to modify the Lewis dot structure model to represent a molecule that's more complex in the real world than we are making it out to be. So on our last couple of slides, we had a look at how we can use the idea of resonance structures to help us better describe species where one single Lewis dot structure does not accurately account for the observed structure and properties of a molecule in nature. And remember, a resonance structure works when you have 2 equally valid or energetically equivalent ways of drawing a Lewis dot structure. But what happens in a situation where you've got 2 different ways of drawing a Lewis dot structure, but they're not equally valid? That is, where one of them, from an energy perspective, seems to make more sense than the other. In that case, obviously, in order to find the lowest potential energy solution to forming a bond, molecules would have a preference of forming one way versus another. And to account for that situation where there are differences in terms of which Lewis dot structure is better than another, we're going to take this idea of formal charge to figure out which of the structures is, from an energy perspective, a better solution to our formation of the molecule. And when I define formal charge here, we're going to talk about really formal charge as the difference between the number of valence electrons that would be present in a free atom and the number of electrons which we assign to an atom in the Lewis dot structure of a molecule or ion which we have drawn. When we're accounting for what we mean by assigning electrons to an atom or another, we're going to go ahead and assume that all lone pairs on a given atom are assigned to that particular atom. Whereas if we have bonded pairs of electrons, we're going to go ahead and assign half of the number of electrons in the bonded pairs to each of the atoms involved in the bond. That is, if we've got a single bond, then we're going to assign one electron to each of the two atoms in the bonding pair. If we had a double bond, we would take two electrons, which is half of the total of 4 electrons in the double bond, and assign those to each of the atoms in the bonding pair. So again, that idea of formal charge is really just a way of keeping track of how many electrons are present in a species around each atom as compared to how many electrons those atoms would have under normal circumstances were they not bonded and part of the molecule. And the general key idea is that the sum of all the formal charges on each atom in a species must equal the total charge on that species. So if we have a molecule, because molecules have 0 net charge overall, the sum of all the formal charges on the atoms must equal 0. So to explore this idea, let's go ahead and have a look at an example here and draw a Lewis dot structure for a molecule of ozone, that is O3. We're going to go ahead and start by counting up our valence electrons. There are 3 oxygens, each of which have 6 valence electrons, which gives us a total of 18 valence electrons available to form bonds. And we'll draw a skeletal structure here. Ozone is a molecule where we've got 3 oxygen atoms, and we'll go ahead and line them up here. 1, 2, 3. And put a single bond between the 2 of them right here, which gives us a total of 4 electrons we have used up to make those 2 single bonds, bringing us down to 14 electrons available in order to fulfill the octet rules for all 3 of those oxygen atoms. Now, if we count up the number of electrons which we need to fulfill the octet rule, the oxygen on the left side needs 6, the central oxygen needs 4, and on the right side we again need 6, for a total of 16 electrons which we need to fulfill the octet rule. And as before, if there's not enough electrons to go around, our solution is double bonds. We just need 1 double bond right now. So I'll go ahead and throw a double bond between these 2 oxygens right here, recognizing that I'm going to find myself in a resonance situation because there's no real reason to give that electron pair to one of the oxygens versus the other. And I can now go ahead and, that I've taken care of that extra bond using up 2 more electrons, fulfill the octet rule by distributing lone pairs of electrons to the oxygen atoms to go ahead and get my valid Lewis dot structure. So I've got a valid Lewis dot structure right now. Let's go ahead and see how the formal charge on each of those oxygens plays out in this situation. Remember again, formal charge is the difference between the number of valence electrons that would be present in a free atom and the number of electrons that we assign to an atom in the Lewis dot structure that we've drawn right here. In a free oxygen atom, we would have, obviously, 6 valence electrons. And let's go ahead and count up how many are assigned to each of the oxygens in our structure we've drawn. For the oxygen on the left-hand side, where I've put the double bond right there, we have, looks like 2 lone pairs of electrons. Remember, lone pairs get entirely assigned to the oxygen atom that they are on. So that's a total of 4 electrons. And then we've got a double bond right there, which means that we're assigning 1 electron out of each of those double bonds to the oxygen atom on the left, which is a total of 2 electrons. So we've got 6 electrons we're assigning to this atom. The formal charge then on that left oxygen atom must therefore be 0, because as a free atom, oxygen would have 6 valence electrons. Within this molecule, we are assigning 6 of those electrons to this oxygen. So the difference between what it would have as a free atom and what it has in the molecule is 0 difference, 6 versus 6. But check out that central oxygen atom right now. The central oxygen atom has, let's see here, 1 lone pair for a total of 2 electrons assigned to it. And then we've got 3 bonded pairs of electrons, and we're going to split the bonded pair electrons between the atoms involved. So 3 bonded pairs means only 3 electrons get assigned out of those bonded pairs, for a total of 2 plus the 3 is 5 electrons assigned to that oxygen atom. So if this oxygen atom has 5 electrons assigned to it, but as a neutral free atom, it would have 6. That means we have 1 fewer negatively charged electron on that oxygen atom assigned to it in the molecule than it would have as a free atom, which means that therefore the formal charge on that central oxygen atom would be a +1. That it has 1 less negatively charged electron than it would in a free state. And last, let's go ahead and have a look at the oxygen on the right. We've got 3 lone pairs, all of which get assigned to the oxygen on the right for a total of 6. And then we're going to split that 1 bonded pair that's sharing which would give us 7 electrons assigned to the right-hand oxygen atom right there. So we've got 7 assigned, but in a neutral state as a free atom, it would have 6 valence electrons, which means we've got 1 extra negatively charged electron on this oxygen in comparison to what it would have in a free state. And therefore, the formal charge on the oxygen on the right is -1. So we've got 0 for the oxygen on the left, +1 for the central oxygen, -1 for the oxygen on the right in this particular Lewis dot structure which we have drawn. And note here that importantly, the sum of the formal charges on all of the atoms is 0, which is equivalent to the total charge on the molecular species, which again is a neutrally charged molecule. So that's the idea about how we assign formal charges. On our next slide, we'll look at how we can use that idea of formal charge to determine which of a set of 2 different Lewis dot structures is the better and more accurately describes the nature of a molecule. So let's go ahead next and have a look at example 4 here, in which we're going to draw a Lewis dot structure for the sulfate ion, that is the SO4 2 negative polyatomic ion. I'm going to go ahead and walk you through drawing 2 different Lewis dot structures for this ion, both of which satisfy all of the rules for a Lewis dot structure. And then we're going to use the idea of formal charge in order to distinguish between which of the 2 more accurately represents the nature of this ion we would expect to see in reality. A couple of conventions that we're going to use here, applying for formal charge as we use it as a tool for determining which of the Lewis dot structures is better. Number 1, a smaller formal charge is preferable if possible. If you have 2 different Lewis dot structures, one of which gives formal charges of, let's say, +2 and -3, and another that gives formal charges of 0, it makes more sense to expect the Lewis dot structure with the small formal charges to be a more accurate representation of what we would see in the real world, since building up charge in one part of the molecule or another really is a way of raising the potential energy of the species. So again, we expect to see smaller formal charges as being preferable to larger formal charges. And in the event that we have a negative formal charge on some place, we should place the negative formal charge on the most electronegative atoms possible, if that is a possibility. Again, because electronegativity is a reflection of the ability of an atom to attract electrons to itself, it seems logical that the more electronegative the atom is, the more likely it is to pull more of that negative charge towards itself. So, with those conventions, let's go ahead now and have a look at the sulfate ion. We're going to go ahead and start by counting up our electrons present here. Sulfur, there's 1 sulfur atom here with 6 valence electrons, and 4 oxygen atoms also which have 6 electrons apiece for a total of 24. And then note again here that this is a -2 charge anion, so we need to add 2 additional electrons to account for the charge on our anion here. That gives us a total sum of 32 electrons available with which to form bonds here. We'll go ahead and draw our skeletal structure. Sulfur, being larger and less electronegative, goes at the center, and we're going to place those 4 oxygens around the outside. And we'll go ahead and add single bonds between the sulfur and each of the oxygens respectively to form our skeletal structure, which uses up a total of 8 electrons to make those 4 single bonds, and we now have a completed skeletal structure, leaving us with 24 more electrons left to go. Now, last year, before we had taught you about the conventions of formal charge, at this point, you would have counted up the number of electrons we still need, which is, we got 4 of those oxygens, each of which need 6 electrons left for a total of 24. And it appears that sulfur already has a full octet, so we can go ahead and then distribute each of those electrons as lone pairs around the outside of the oxygens, which leaves us with none left over. So it looks like we've got a nice Lewis dot structure drawn right here. So far, so good. But let's go ahead and take a look at an alternate Lewis dot structure we might also consider drawing. We'll go ahead and start with the same, obviously, number of electrons. We'll use the same skeletal structure. But rather than this time going ahead and distributing all of those lone pairs around the outside to the oxygens, instead, I'm going to go ahead and draw a set of double bonds to 2 of the different oxygen atoms. And as I make that set of double bonds right here, you might think to yourself, well, wait a minute, what are you doing? You're violating the octet rule. First thing to recognize is, yeah, I am violating the octet rule in doing that, but remember, sulfur is an element in period 3 or below, which means it can form an expanded octet. And even though we've told you that the octet rule tends to be followed by these species here, remember it's an octet rule. It is not necessarily a rule that does not get violated. We've seen in many different cases that there are species that will violate the octet rule if it lowers the overall potential energy of the molecule to do so. So I'm going to go ahead and make that extra 2 sets of double bonds right there, and go ahead now and count up the electrons which we have remaining that need to be distributed still. And you see we can still fulfill the octets as we count up here with the number of electrons which we have left over. Now, as I do that, we can check to see why I might have considered this as an option. Have a look at the first Lewis dot structure we drew right there, that is with only single bonds. If we want to determine the formal charge on each of the elements present right here, have a look first at the sulfur in the center. The sulfur in the center as a atom by itself would have 6 valence electrons. We've got 4 bonds to this sulfur, and we're going to again assign 1 electron out of each bonded pair there to that sulfur, which gives us 4 electrons the sulfur atom has assigned to it. So that would imply it has 2 fewer electrons than it would have assigned to it if it was an atom by itself. And as such, the formal charge on the sulfur here is +2. And have a look at each of those oxygens now. Each of the oxygens has 3 lone pairs for a total of 6, plus 1 out of the bonded pair we assigned to it as well for a total of 7. As an atom by itself, oxygen would have a total of 6 valence electrons, which implies each of those oxygens has 1 extra electron assigned to it right now, which gives them all a formal charge of -1. So we've got 4 -1 formal charges in the oxygens and 1 + 2 on the sulfur. And again, we check our rules. Remember, the sum of the formal charges must equal the overall charge on the species, which is 4 -1s + 2 gives me the -2 charge overall in the sulfate ion. So yeah, that checks out. That's a valid Lewis dot structure. But now have a look at the second Lewis dot structure we drew with those 2 double bonds. Just as in our first structure, the 2 oxygens with the single bonds to them have 7 electrons assigned to them right now, 3 lone pairs and then 1/2 of the bonded pair. And again, that gives each of those 2 oxygens, again, a formal charge of -1. But have a look now at the 2 oxygens with the double bonds. Each of those 2 oxygens with the double bonds have 2 lone pairs for a total of 4, plus 2 bonded pairs, each of which assigns them 1 electron for a total of 6, which means those oxygen atoms have exactly the same number of electrons as they would have as an atom by themselves, which gives them a formal charge of 0. And that sulfur in the center also now has 6 bonded pairs of electrons around the outside. Again, we assign 1 of the electrons of the bonded pair to the sulfur, which means the sulfur also has a formal charge of 0, 6 electrons assigned to it as it would have as an element by itself as well. So at this point now, our Lewis dot structure with the double bonds has still the sum of the formal charges is -2, but the formal charges now are smaller than they were before, with just 2 -1s instead of, in the first option, we had 4 -1 formal charges on the oxygens and then that 1 + 2 on the sulfur. So by our convention that the smaller formal charges represent a lower potential energy state, it seems like we would expect that this actual configuration is energetically more favorable than the one which we would have drawn last year, which simply just fulfilled the octet rule. And as a little quick side note here again, note that there's really no reason to give 2 of the oxygens double bonds and 2 single bonds over another, so we really could represent this better with a resonance structure as well, showing that this ion is better represented by a blend or a superimposition of multiple different Lewis dot structures, each of which is equally valid as long as we keep those 2 double bonds in there in those different structures. So if we actually look in nature and see the real structure of this ion, by measuring bond lengths and making some comparisons of what they would be as single bonds versus some sort of resonance structure with bond density greater than a single bond, which would represent some double bonding taking place here, or at least a resonance structure with double bonds distributed amongst the different positions that they could exist here. Yeah, it seems like the actual nature prefers the Lewis dot structure that we have drawn here with those double bonds. So again, Lewis dot structures have limitations, but by understanding both resonance and formal charge, we can make our model into a better representation of what we observe in nature than it would be if we simply just followed the initial rules we had given you last year. So that is it for this portion of our lecture right here. As a big kind of overall reminder, just please make sure on the actual AP test to take the time to go through the steps in solving those Lewis dot structure problems and use formal charge as a guide in order to distinguish which would give you the best possible Lewis dot structure to represent what we would observe in nature. Thanks for listening.